Okay, so for example, here we have you push a crate of mass 50 kilogram, okay, horizontally with a force equals to 400 Newton along a rough surface with a friction coefficient of 0.30, and then it makes a displacement of 30 meter. Okay, how much work done on the crate? Okay, so as you can see on this example, so we have that you are pushing up, like writing is better. Okay, so you have a crate. Okay, you apply a pushing force of 400. Okay, so you apply a pushing force. I will look at that value. Okay, and you are told that on that surface here there is a friction force. So as I said, the friction force is always opposing the force. So we have a friction force. As you apply this force, then there is a friction force on that direction. Okay, so this is a force applied. Okay, then this is the friction force, which is always opposing the motion. Okay, so on that body, as I said, you always have the normal force, and we always have the weight. Okay, so remember from our previous definitions, we have that friction force is equals to the coefficient of the friction times what? Times the normal force. What do we have here? What is our normal force? Our normal force, if we apply the Newton's second law, it says that the normal force, because this is our positive now, if you assume that up one is our positive and then down one is our negative. So we have normal force minus the weight, since this object is not going to move in the vertical, is equals to 0. Okay, so therefore we have here that our normal force is equals to the weight. Okay, so therefore our friction force is going to be equals to the coefficient of the friction times the normal force, which is going to be equals to the frictional coefficient times the weight, where our weight is equals to the mg. Okay, so because this weight is due to the gravitational acceleration, so we have the mass times the gravitational acceleration. So we can calculate what our frictional force is. Okay, then the work done, the only two forces that are acting in parallel here, because if this object is moved, because they are saying that you make a displacement from that position to that position, a displacement equals to 10 meters. Okay, so which means the work done, remember our equation, it says the work done, okay, it equals to the force times the distance, the displacement, because since these forces are parallel, we don't need to worry about that. So just use that. And since here now we have two forces, okay, so it means we have to get the net force applied, because on the crate here there are two forces acting: the force that you are applying and the force which is opposing the force that you are applying. So therefore the net force, the net work done is equals to the what? To the net forces acting on that the net forces acting on that times the displacement, or we can simply say is equals to the work done by what? By the force applied, okay, minus, because the frictional force, the work done by the frictional force, it's negative, minus the work done by the frictional force. Okay, so you can either calculate what is our normal force. We are given what is our force applied, is given on the question. Okay, so we can calculate what is our friction force, okay, which is given as 0.30 times the mass. Let me just check for values. So we are given that a mass is 50 kilogram, okay, and the displacement is 10. Okay, so it means this is a 50 kilogram times the mass times the 9.8 or 10, whatever values that you use, or 10, depending on what you are given, the gravitational acceleration. This is the gravitational acceleration. Okay, so it's equals to what? So if we take 0.30, where's my calculator now? Okay, so if we take 0.30 times 50 times 9.8, we have that is equals to 147 Newton. Okay, and we are given this is 400 Newton. Okay, so we can go on. We know that the work done, it's equals to the summation, or it's equal to the work done by the force applied, okay, plus the work done by the frictional force. Okay, and we have, so it means, because the work done by the force applied is equals to the force applied times what? Times the displacement. And the work done by the frictional force is equals to the force, frictional force times the displacement. So if we substitute in that one there, so we have that this is equal to the force applied times the displacement plus the work, which is the force done by the friction force times the displacement. Okay, remember that the direction of the frictional force is always negative, because it's always oppose the motions, depending on which one did you take your axis. So if we take now, in our case, we take our positive to be on the left. Okay, so on the right to be our positive x-axis. So it means we have our force applied minus, so I can put this as a displacement here. Okay, this is just a directions. Okay, and then this one here minus, because the frictional force is negative. Okay, so we have minus the frictional force. I can that one factor that one out times what? The displacement. So I can substitute over my values. I know what my force is applied is, which is 400. I know what my frictional force is, which is 147. And I know what my displacement is, which is 10 meters. So doing that, we have that the work done on the crate, it equals to 25,300 joules. Okay, so you know, or you can just calculate this one here. Calculate what is the work done by the frictional force, what is the work done by the force applied, and then you simply plug in there by using that formula, and then you have your answer. It will yield to the same answer because we are doing the same thing. Okay, so this is what we have there. So here, the normal force and the weight does not work to this, because you can see also here that here it's all number one, there is no displacement in vertical components. Number two, the normal force and the weight are perpendicular to the displacement. So therefore, these two forces, the normal force and the weight, does not work in here. Okay, so another example here is you carry, okay, a 20 kilogram box, a horizontal distance of that. How much did you do on the, how much work did you do on the box? Okay, so this one here, it's just almost the same. Okay, this is you standing there, you have a box on your hands. Okay, you carry this box from, okay, so you carry this box, it's you are just carrying this box. Okay, so and then so how much work did you do, okay, on box? Remember that we draw. Okay, so this is just the force that you are applying, the one that you are carrying with. Okay, so if I carry this, okay, I am just moving here, I am at this position, and then I am just moving along, this is myself, and I am just moving along with the box, or the same my box is on the hand, I'm just the one who's moving. So how much work did you apply? Okay, so you are this is a force that you are putting on there. So remember now, this is a displacement that you are okay, so this is the box, and this is just you carrying up this box. Okay, so it means you're carrying up on the vertical, so you have a normal force and you have weight, and you do a displacement. Okay, so how much did you do on the box? Okay, so what is happening? So so you see that Okay, so how much work did you do? So here you can see that. Okay, so you are on your hands. The box is on your hand, and it's you who is walking, not it's you who is making up the displacement. Okay, so you have that the box. Okay, so this is your hand, and you are just moving from this position to that position. Okay, so that displacement there. Okay, so the box is not doing anything. You are not applying any force onto the box. It's only the how will I say it? Like you are pushing or doing what? The only force that you are applying is the one which is coming from your hand, on top of your hand, to this, coming from your hands here, just to the one which is helping you, the box not to fall. Okay, so I can say that is a normal force. I can say, okay, you are applying a force which is coming from your hand. In which direction? In that direction there. Okay, because that force that you are applying on that box is just to help it to be unstable. Okay, so the box is not moving, it's you who is moving. So what is the force? How much work did you do? Okay, how much work did you do on the box? Okay, you are moving up here, the box being on your hands. Okay, so it means that the force that you are applying on the box, okay, this force that you are applying, as you can see here, this is the force that you are applying. Okay, and this is the displacement that you are causing. As you are moving, the box also moves along with you. Okay, so you see that the force that you are applying to the box is what? It's perpendicular to the displacement. Okay, so even if you by applying that, I can say work done is equal to the force times the displacement times the angle, cosine of the angle. Okay, your angle is perpendicular, so your angle is equals to a 90 degree. So therefore, if I put in there our cosine, so our cosine of 90 degree is equals to 0. So therefore, this part goes to 0. So the work done that you do onto the box is equals to 0. Without even going through the calculations, as I've said, that if the force is perpendicular to the displacement, then there is no work done to an object due to that perpendicular force. Okay, so these are just the exercises to go through. You can go through these exercises, and then it will help you to understand. Unless you have questions before we go through. You don't have questions? Should I continue?
No, I do. Can you go back to, can you explain a little bit about the crate?
The one
The example of, about
is
the crate, the example that you gave us about the crate.
the one where you are pushing up with 400.
Yes.
Okay. Okay, so the question is saying you are pushing a crate. Okay, so you push a crate of 50 kilogram horizontally with a 400 along a rough surface that has a coefficient of friction with equals to 0.30, and the displacement that you cause is 10 meter. Then how much work, okay, or what is the work done on the crate? Okay, so the work done on the crate, okay, so this is the crate. Okay, the crate, they are saying you are pushing that crate. Okay, so this is the force that you are using to push. So this is the force that you are using to push that crate. Okay, so on the surface where this crate is, there is friction. Okay, due to that friction surface, then that means there is a friction force that is going to oppose this force that you are applying. Okay, so as the crate is moving, as you move this crate, okay, with the force that you are applying in that direction, as you move it along, okay, there is a force on this surface which is opposing that motion. Okay, so you always say that there is a perpendicular force, which is a normal force, the one which reacts to the weight. Okay, so now all these forces here, they are acting on the what? They are acting on the crate. Okay, so the forces that are acting on the vertical component does not work to this crate because they are perpendicular to the displacement. Remember, you are moving up the crate from here, let me say up to there. Okay, so this crate moves. The distance that it moves with, or the displacement it causes, is equals to 10 meters. This is the displacement. Okay, then okay, so the work done on the vertical forces does not work here because the forces here, these ones, they are perpendicular to the displacement. So we don't actually need them, but we need them to calculate what is, because we are not given what is our friction force. But remember that our friction force, when we defined it as equals to the coefficient of the of the friction times what? Times the normal force. So what is the normal force? The normal force here, if we sum up those the forces acting in the y component, the normal force is equals to, so it's the normal force minus what? Minus the weight, which is equals to 0, because there is no acceleration. It's not moving in the y component, it's only moving up in the horizontal components. So therefore the normal force is equals to the weight. Okay, so it means when we calculate our weights, we say it's equal to the mass times the gravitational acceleration, because this weight is due to the gravitational acceleration. So putting in these values there, we have the kinetic friction times the normal force, which is equals to the mass times the gravitational acceleration. Okay, so since this object will only accelerate, will only move in the horizontal component, so the work done on this object will be equals to what? The net, okay, the work done on the crate is equals to the summation of the, we sum up all the forces that are acting, is equals to this summation of the work done by the individual force which is acting on the crate. So, and the forces that does work here is only the force that you apply as you are pushing, and the frictional force which oppose the force that you are using to cause the motion. Okay, so it means you are simply summing up all the work done there. So it means this is equals to the work done by what? By the force that you are pushing with, plus the work done by the friction force. Is it clear up to there?
Yes.
Okay, so and we say that we define the work done as what? The work done is defined as the force times the displacement. We can just forget about the angles because they are already parallel. We can include it if we want, not really necessary. Okay, so what is the work done by the force applied? The work done by the force applied is equals to the force applied times the displacement it's causing. Remember, the angle there is 0. It's in that direction. Okay, so this is the force applied, so the angle here is equals to 0. So therefore, the cos of 0 is equals to what? 1. So these forces are already, because they are parallel. Okay, so what is the work done by the friction force? The work done by the friction force is the negative friction force, the force applied by the friction force, the force due to the friction times the displacement. And remember, the direction of the force is in that direction. The friction force is in that direction. Okay, where the angle there is equals to 180. So what is the cos of angle 180? The cos of the angle 180 is equals to -1. So if we put this into that equation, we have that force due to the work done due to the frictional force is equals to that one there. Okay, so therefore the total work done on that on the crate, okay, is equals to, you sum up all these forces as I said, so it's equals to the work done by the force applied plus the work done by the friction force. Okay, so the work done by the applied force is force applied times the displacement. What is the work done applied by the friction force? The work done applied by the friction force is a minus friction force times the displacement. So I can simply factor out the displacement and then I just say, okay, the force applied minus the friction force is equals to the times the displacement, gives me work. So what is this one here? This one is it's just the net force in the x direction. So if you want to go on, you can say, okay, this one is the net force, or you just simply substitute this. If you not calculate what the net force is, then you simply have the force applied is saying is 600. It's 400 Newton, minus we have calculated what our friction force is. which is 147. Then we multiply this one with the displacement of 10 meters. Okay, so it's 400 minus 147. Then we multiply that with 10, which gives us, oh, it's even 2,300. So there was something wrong that we did previously. So it's 2,530 joules. Is it clear?
Yes, you can go on.
Okay, so that's how we calculate our. Okay, so we have talked about the work. Now we are going to check about the energy. So what is really energy? We are always talking of energy. I don't have energy. I don't know what. Okay, so energy is the capacity, or I can say the ability to do work. Okay, so the ability of the body to do work is what is called the energy. And the unit of energy is the same as the unit of the work, which is simply also joules. Okay, so we have many different forms of energy, such as mechanical energy, light energy, sound energy, magnetic, electricals, and so forth. You can mention them. But the two energies that are related with motions are potential energy and the kinetic energy. So we look at the kinetic energy first before we move on to the potential energy, and we will see how does this relates, how does the kinetic energy relates to, or how does the work and the energy relates to one another. Okay, so as we said that the energy is the ability to do work. So when positive work is done, as you know, so if we have a positive work, it's done on the object, then you see that the speed increases. Remember, we say that if work is positive, then it means the net force is greater than the, the force applied is greater than that. So when you have a work, the work done on the object is greater, then the speed of that object increases. As you can see here, you have a demonstration of an apple. As this apple is falling down from the due to the gravitational acceleration, so then it's causing from where it was, it's just falling down. It's causing up a displacement. Since the force, so the force or the weight is in the same, or in the parallel, it's parallel to the displacement, then in the same direction, then we have a positive force. So, and remember from our free falls and projectile, we say that as the body goes up, the speed tends to decrease. Okay, and when the body goes down, its speed increases. Okay, so this is almost that's what we are talking about here. So here you can see that actually here the distance, the speed, the displacement is decreasing. Is just coming from the higher level going down. Okay, while on this one, if you have a negative work done, okay, so you can see that then the work done due to the gravitational is in the opposite direction of the displacement. Okay, so the displacement is up while the force is going down. So okay, so here we see that the displacement is increasing, but the speed is decreasing. So the negative work done, the negative work done decrease the speed. Okay. So we remember we were talking about the kinetic frictions, and then we say that the kinetic relates to the motions. Okay, so the kinetic energy is the energy due to the mass and the velocity of the moving object. So in other words, the kinetic energy, it's the energy of the body being in motions. Okay, so if we have the kinetic energy of an object of a specified mass in an amount, it travels at a specific velocity. So if you know what the initial velocity is, or the velocity that the object is traveling with, it's actually equals to the, we can able to calculate what is the equals to the kinetic energy. So let's see how to calculate the kinetic energy. Let me say I don't know the equation. Someone just out of the blue comes and then doesn't know how to get, so we can see how to calculate the energy. So let's say you consider an object of the moving, okay, of mass m, and it's moving up in a straight line with the initial speed. So like it starts with the initial speed equals to v naught, and it accelerates uniformly to a speed, final speed can say equals to v. Okay, then a net force is exerted parallel to its motions over the distance. Okay, so remember, so what we are saying here is, okay, you have an object moving at this position. We have that these objects have the initial velocity. Okay, as it moves, this is having a mass m. Okay, it moves at a certain distance or displacement, and moving with a speed at this point. Okay, I can say the velocity at that point is equals to the v. Okay, so this is there, as it's on this point, is moving up at a constant velocity v. This is the same object of the same mass. Then, since this object is moving, then is associated with what? With the force. It means there is a force applied or occupying on this object. In order for it to move, it means there should be a force applied. Okay, so if, let me see, apply that, if there's a net force on this, let me just say the net force, okay, acting on that object is what we have as the net force. Okay, so it means this object is moving under the influence of that net force. So from Newton's second law, you are saying that force is equals to the mass times what? Times the acceleration. So, and we define that the work done is equals to the force times the displacement times the distance it covers. So how much work is done by this object as it moves from this position, moving with initial velocity, to that position with that velocity under the influence of that net force. Okay, so here we have our force. So it means our force is equals to the mass times in acceleration times what? Times the displacement. From Newton's second law, we say we have that the final velocity squared is equals to I mean, from the kinematics, we defined that if we want to know what is this the speed, we see that the final speed here is equal to the initial speed squared plus 2 times the acceleration times the displacement. So if I solve this, let me solve for my, what is my acceleration times the displacement? So if I solve it, I have that v in the final velocity squared minus the initial velocity squared, divide this by 2 is equals to the acceleration times the displacement. So if I know this, then I can substitute it there. Okay, so it means that my work done due by the object in motion, it's related to the mass of an object in motion times what? Times it is final velocity squared minus it is initial velocity squared divided by 2. So if I I multiply this one out, then I have something like, okay, factoring this out, we have work is equals to the mass. Okay, we have v naught, I mean the v final, the final velocity squared divided by 2 minus the initial velocity squared divided by 2 times the mass. What do I have? So it means I am getting something that my kinetic energy, I mean my work done, okay, so it means I am getting something that my work done is equals to a certain quantity. Okay, if the object is moving, then it means that my net work done, my work done on that object is equals to the change in the quantity in the form of that value there. So what are these values? What are these? What is this value that we get? Because you see that we are getting that, okay, my work done is equal to the mass times the velocity, I mean the speed, final speed divided by 2 minus the initial speed squared divided by 2 times m. So it means there is a quantity, which means my work done by the object which is moving is equals to the something of it is speed squared divided by 2. So it means I have this quantity times it is speed squared. So what is this? So this one, this quantity is what is called, since it is in motions and this one is related to the energy, is what we call the kinetic energy. So it means it's the energy of an object in motion. Okay, so if I have that, so it means I can write this as work done is equals to the, if this is now kinetic energy and this is the final speed, which means it's equals to the kinetic energy final, the one at final speed, minus the what? The kinetic energy initial. It is simply equals to the change in kinetic energy. So it means that work done by the object moving is related to energy by that equation. Work equals to the change in kinetic energy. What does this tell us? Okay, so it means this tells us that, or this gives us what we call as a work energy principles or work energy theorem. Why is it called like that? It says that the work, how it shows us how does the work and energy relate to each other. Okay, so this is simply what we have. So this form, or simply that form, is called the work energy theorem or work energy principles. Okay, so the work energy holds for both positive and negative work done. Okay, when do I have so here it says if, okay, so if you have a positive work done, then which means that that value, the difference, the change in the kinetic energy is greater than 0. So it means that your final kinetic energy is greater than the initial kinetic energy. So, which means that the object final speed, okay, so the object final speed is greater than the object initial speed. If we look back at our diagram that we have when we defined energy, we said that if you have a work which is positive, then the speed or the object speed up. So it means the final speed of the object increases when you have the when you have a work energy, when you have a work which is positive. While if work is negative, when you have a negative work done, then that means the change in kinetic energy is actually less than 0. Why does it mean? What it means is that the final energy is less than the initial kinetic energy. So it means the speed decreases as the object is moving. So it's like the final speed is less than the initial speed. Okay, so which okay, so which means, okay, so what does this one shows us? It says that so when the body slows down, okay, it's actually release energy. So that is why we have the energy that being negative. While when the object is speeding up, it's actually gaining more energy. Okay, so as the body slows down, it releases that energy, the one that we have here. So it's the one that we have. So you can see here that as this object slows down, come on. As you can see on this equation, just use this equation here. As you can see on this equation here, if let me say I calculate what is the kinetic energy final if my work done is equals to negative. Okay, so you'll see that if I have my if my work done is negative, if work is negative, okay, then you see that, okay, so we have that from our work energy theorem. So we see that minus work is equals to the change in kinetic energy, which is saying that the kinetic energy final minus the kinetic energy initial. Okay, so if I want what is my kinetic energy final as this object, as we have a negative work done on that object. So we have that. If I move that into this, then I have that the kinetic energy initial, you are actually subtracting out the work done. So this one gives us the what is the energy final. So you see that here the work done when it is negative, so that kinetic energy, the final kinetic energy is less than, because you can see we are taking out something from the initial kinetic energy. So the final kinetic energy is less than that amount. So it means as the object is slowing down, it releases that energy. Okay, so well, this one thing to note that when you have a negative work done, the speed slows down. As you can see here, the object tends to slow down. So as it's slowing down, okay, so it equals to the work done of the net slowing forces. So it simply equals to the forces that are opposing that object. So it's just that we need to keep in mind that when you have a positive work done, then the final speed of that object is greater than the initial speed. Okay, while when you have a negative work done, the objects tend to slow down. It releases actually the energy. So the other part is this one here, it gains more energy as it goes down, while the other one, it releases the energy. You can say it loses energy, while the other one, it gains energy. Okay, so like I think we have an example. I have an example here. Okay, so you have an example here. Okay, but it's fine. Okay, a 140 kilogram baseball is thrown up with that speed of 25 meter per second. Then the question is asked, what is its kinetic energy and how much work was done on the ball to make it reach this speed if it started from rest? Okay, so we are given that it's the object is thrown up. Okay, so the object is thrown up. Yeah, so it's thrown up with a speed of that. Okay, so it goes up. Okay, so you have an object, okay, thrown up with the speed equals to 25 meter per second. Then it's asking what is its kinetic energy. So remember we say that the kinetic energy is equals to half times the mass times the speed squared. So we know that a mass is 140 gram. Remember, we have to convert this to kilogram. Whenever we are doing calculations, we have to make use of the SI units. Okay, so this is equals to a half of 145 gram divided by 1000 gram per kg, and we multiply this with the velocity given, which is 25. Let us not forget to square that value. Okay, so if we have that this is 145, you must divide it with 1,000, convert it to kilogram, multiply that with 25 squared, then we divide this by 2. So therefore the kinetic energy is equals to 45.3 joules. Okay, so we need two significance, our rules, same significance as the least, so it's simply 45 joules. Okay, then the second question, is how much work was done on the ball to make it reach this speed if it started from rest. Okay, so if this ball, okay, if this was the final speed, okay, and this ball started from rest, okay, it was not moving, and that's what it means that the initial velocity at the rest is equals to 0. Okay, so therefore from our work theorem, it says that the work done is equal to the change in kinetic energy. So it's saying that the kinetic energy at final minus the kinetic energy initial, okay, equals to that work done on that object. So therefore, what is our work done here? So our work done is equals to 45 joules minus, because this is the kinetic energy done at that speed, okay, minus the initial kinetic energy is equals to, which is equals to 0. Okay, so it means it simply equals to 45 joules. Okay, so you'll see that it starts at 0 and then it goes up to the velocity. So it starts with the velocity 0. This is the initial velocity, and its speed increase to 25 meter per second. Okay, so it means the work done, the work done is equals to 45. You can also check by making, is this positive work done or negative work done? By remembering that if the speed increases, then the work done is positive. If the speed decreases, then the work done is negative. Okay, so by keeping in mind, let me say if this was 25 and then it ends at 0. So it means our final speed, our final kinetic energy, if this was the case, it starts with a 25 and then it's at that point after the state, as it moves up or whatsoever thrown up, the final velocity is equals to 0. If that final velocity is equals to 0, if we substitute it in there, this one becomes its initial speed, and then you can see that, it is initial kinetic energy, and you see that 0 minus 45 equals to that. Sometimes you also need to verify just to check, is it my values making sense or not? Okay, so you have to be careful also in what you are doing. Okay, so another question is, how much work is required to accelerate a car, to accelerate a 1,000 kilogram car from 20 meter per second to 30 meter per second? Okay, so you have a car, okay, of 1 of mass equals to 1,000, okay, 1,000 kilogram, and it is initial, okay, it has a velocity, okay, so change in velocity, why am I squaring? Change in, so it is initial velocity was 20, it's saying from that to that, so meter per second, to the final speed of 30 meter per second. Okay, so how much work is required to accelerate from this speed to that speed? Okay, keep in mind that you don't say, okay, remember that first, remember that the work energy is equals to the change in what? Change in the kinetic energy, where this is equals to the final kinetic energy, the final minus the initial kinetic energy. Okay, so which is equals to the half mass times the final squared minus the half initial squared. Okay, so this one, so you don't subtract V minus the V naught. This is wrong. If you do V minus V naught, this is not equals to that value there. Okay, but you can subtract V squared minus, so you can find what is the change in the velocity squared. So I can do this and say, okay, this is the same as a half, factor out my mass, so it's the same as the velocity squared, I mean the final speed squared minus the initial squared. Okay, so this one can work, but this one cannot. So don't subtract the velocity first and then you square them. Okay, so this one is not equals to that minus that one squared. Okay, so this one won't give you that. Okay, so if you put in our values, we know half, we know what our mass is. It's saying is 1,000 kilogram. We don't need to convert, it's already in the SI units. The velocity, the speed is equals to the final squared minus the initial, which is 20 squared. So this one gives us that value. Okay, so 30 squared minus 20 squared equals to times 1,000 divided by 2. Okay, so we get something like 2.5 times 10 power 1, 2, 3, 4, 5 times 10 power 5 joules. Or you can simply calculate what is my kinetic energy. What is my kinetic energy final, and what is my initial kinetic energy. Okay, so this one says the same. So I substitute these values there. Okay, so kinetic energy final will just be equals to the half times mass times the final speed, which is half times 1000 times the velocity squared, which is 30, times the 30 squared gives us, okay, so that gives us 1000 divided by 2 times 30 squared, which is 45, so it's 4.5 times 10 power 1, 2, 3, 4, 5 times 10 power 5 joules, and the final initial kinetic energy equals to half times the mass times the initial speed squared, is equals to the half times 1000 times 20 squared. That gives us 20 squared times 1000 divided by 2 gives us 2.0 times 10 power 5 joules. Okay, so going on and take work is equals to the change in the kinetic energy. Okay, so putting in these ones is equal to the kinetic energy final minus the kinetic energy initial. This one gives us 4.5 times 10 power 5. Then we subtract out that 2.0 times 10 power 5, and then we get 2.5 times 10 power 5. So whatever you do, it's all the same. Just be careful that you always square and you don't subtract first the velocities and then you square them later, because it is not equal. Okay, unless you have questions. Do you have questions?
No,
Okay. So
I think, yeah, it's quite better.
okay, so we can start with next time with potential energy.
Okay, miss. Can you